Okay, so we have another capacitor problem where we have spherical shells. So it says a capacitor is composed of two concentric spherical shells of radii A and B respectively. They have equal and opposite charges as shown above. So the inside shell has positive Q, outside shell has negative Q. Just outside the surface of the inner shell, the electric field is directly radially outward and has magnitude of E naught. So part A, with the use of Gauss's law, we want to express the charge Q on the inner shell as a function of E naught and A, where E naught is the electric field right on the surface. Okay, so setting up Gauss's law for part A. So looking at this picture here, this is a little bit different of a use of Gauss's law. So we really want to set up a Gaussian surface that is exactly equal to the radius of the surface of the inner shell here. So basically, the radius that we would use is equal to a, and so setting up Gauss's law, we have surface integral E dot dA is going to be equal to Q inside over epsilon naught. Okay, and typically we would have, so we would end up with uh, electric field times the area of our Gaussian surface, so the area of our sphere. This equals Q inside over epsilon naught, which the amount of charge inside of that is just Q over epsilon naught. The electric field, or the area here, was typically E times 4 pi little r squared, which equals Q over epsilon naught. But at exactly r is equal to a, the electric field is E naught. So they're telling us what the electric field is at that point. So we're going to replace those values over here and then solve for Q. So at r is equal to a, so we'll have 4 pi. Instead of r, we'll have a squared. And then instead of E, we know the value of E, it's E naught. So we have E naught 4 pi a squared. This is equal to Q divided by epsilon naught. And then to solve for Q, we're just going to multiply both sides by epsilon naught. So we get Q is equal to E naught times a 4 pi epsilon naught a squared. Be careful that you do not confuse E naught and epsilon naught. They look similar. Part B says to write an expression for the electric field strength E between the shells as a function of E naught, A, and R. So we kind of set this up using Gauss's law. So for part B, we already set this up, but now we know what the charge is equal to. We know what charge is equal to in terms of those variables that they told us. We know what Q is in terms of E naught and A. And so what we can do then is using this same setup. We have E times, so this is part B. We have E times a 4 pi r squared is equal to Q over epsilon naught. We know what Q is. We found that earlier in terms of E naught and A. And so we're going to have the right side of this equation, we're going to set that equal to E naught, again, the electric field at R is equal to A, times 4 pi epsilon naught a squared, and then that is divided by epsilon naught. And then we are going to solve for E. And so if we do that, so we have E. To do that, we're just dividing both sides by a 4 pi. Dividing both sides by a 4 pi. And if we do that, then this 4 pi goes away. This epsilon naught cancels out with that epsilon naught. And so we are left with E naught times a squared. Oh, sorry, we're dividing both sides by 4 pi r squared. So we'll be left with E naught times a squared over r squared is the electric field. Part C, we want to find the potential difference, V, between the shells as a function of E naught, A, and B. Okay, so we're trying to find the potential difference between this point here and this point here. So we want to know what is delta V, so what is V? Okay, and so to find that, if we already know the electric field, so for part C, if we already know the electric field, which we do, then V is going to be the negative integral, and we're going from point B to point A of E dot dr. And then I can substitute E in for negative integral from B to A, and we have an E naught A squared over R squared dr. Taking out my constants, we have V is equal to negative E naught A squared, and then we have the integral of 1 over R squared is going to be negative 1 over R, so this is times negative 1 over R, and we evaluate this from B to A. Okay, and so the negatives cancel out, and we're left with V is equal to E naught A squared times, and we're going to have a 1 over A minus a 1 over B. So that is the electric potential at that point, or the potential difference between those 2 points, I should say, in terms of A, B, and E naught. Part D says to express the energy U stored in this capacitor as a function of E naught, A, and B. Okay, so part D, choose a different color here. So for part D, the energy stored in a capacitor, there's several different ways to represent this. If you know one way, then you can find all of the other ways out. So energy stored in a capacitor is 1 over 2, so 1/2 times, so one example might be Q squared over C, for example. All right, and so we would use whatever values we know. So I don't know the capacitance, so if I want to rewrite this, I want to get rid of capacitance, but we know that capacitance is going to be, that's charge over voltage. So that's Q over V, for example. And so I can get rid of capacitance in this case. So U of C is equal to, this would be equal to a 1/2, and then we would have a Q times V, it looks like, if I substitute Q over V in for C. There's basically 3 ways to represent the electric potential, or I'm sorry, the energy stored in the capacitor. You just need to change your variables out for either Q, V, or C. So this is what we are going to use because we know these values. So what we're going to end up with is a 1/2, and again, the problem asks us to do it in terms of E naught, A, and B. So we know what Q is. We found that earlier. Q is this right here. We have E naught. We have an E naught 4 pi epsilon naught A squared. And so we'll plug that in down here. So we have a 4 pi epsilon naught A squared for our charge. Oh, I forgot the E naught. E naught 4 pi epsilon naught A squared for our charge. And then for our voltage, we just found that just a minute ago, it's E naught A squared times 1 over A minus 1 over B. Okay, so we're going to times all of this by E naught and then A squared times, we have a 1 over A minus 1 over B. 1 over A minus 1 over B. I'm just going to simplify this just a little bit. I'm going to combine like terms, and then I'll leave it like that. So what I can do here, so the potential energy stored in the capacitor, we're going to have 1/2 times 4 is equal to 2, so we're going to have a 2. I have 2 e naughts, so we'll have a 2 e naught squared. I just have 1 epsilon naught, so I have epsilon naught. I have an a to the fourth, and then so I can write a to the fourth, and then we're going to multiply this by 1 over a minus 1 over b. Okay, and what I can do is just distribute the a to the fourth if I wanted to. I could really distribute all of them, but I'm not going to, and you'll see why here in a minute. So I'm just going to distribute the a to the fourth for now. So we'll have 2 e naught squared epsilon naught, and then we have everything multiplied by a to the fourth divided by a is just a cubed, and then a minus a to the fourth over b. And I'm going to leave that like this. So part E says to determine the value of A that should be chosen in order to maximize U. So we want to pick a value for A so that we get the most energy stored in our capacitor if we let E naught and B stay constant. So we're not going to change those values. Okay, so basically what is the radius that we should pick for our inner shell to make the energy stored in that capacitor the greatest? And so the way you're going to do this, anytime I see maximum, if they tell me to find the maximum of something, I'm thinking derivative and then setting equal to 0 and solving for some variable. So since we're trying to find where the maximum will be in terms of the radius A, what I would do is we are going to, so this is the technique we're going to use to solve this. So to figure this out, we're going to take the derivative of u with respect to a. We're going to set it equal to 0, and then we would solve for a at that point. So that's what we are going to do. So we know u. We have our equation right here. So for the last part here, part E, we are going to take the derivative of u with respect to a. That's the first step. So let's go ahead and do that. So if I take the derivative of u with respect to a, then this is going to be the derivative d by dA of this function here. So we have 2 e naught squared epsilon naught. I feel like I forgot a variable somewhere. Yeah, sorry about this, but we have a pi here that I left out. So that's not going to matter for this next answer, but just so you know, our answer is technically 2 epsilon naught, or 2 e naught squared pi epsilon naught. So we have 2 e naught squared epsilon naught. We have a pi in there, and then what we're going to have is all of this multiplied by a cubed minus a to the fourth over b. All right. I can kind of pull the constants out of this derivative here. I can pull this 2 e naught squared epsilon naught pi, so that I have, so I'm going to have 2 e naught squared epsilon naught pi, and then I have the derivative of just this function, derivative of a cubed minus a to the fourth over b, the derivative of that with respect to a. Okay, and so what I'm left with is 2 e naught squared epsilon naught pi, and then I have the derivative of a cubed is going to be 3a squared, and then I have minus the derivative of a to the fourth over b is going to be 4a cubed over b. Okay, and then, so I took the derivative, and now I want to set this equal to 0, so I'm going to do that. Set this equal to 0, and then I want to solve for a. Okay, so I want to get a all by itself. First thing I'm going to do is divide both sides of the equation by all of this. So I'm going to divide both sides by 2 e naught squared epsilon naught pi, and that just gets rid of it. So 0 divided by 2 e naught squared epsilon naught pi, that just still equals 0. 0 divided by anything or 0 times anything is still 0. And so I'm left with 3a squared, minus 4a cubed over b is equal to 0. I can add the 4a cubed over so that I have 3a squared equals 4a cubed over b. I can divide both sides by a squared so that I'm left with 3 is equal to 4. If I divide this side by a squared, I'm left with just 1. If I divide the right side by a squared, I'm left with 4 times a over b. And then I am going to get a all by itself, so I'll multiply both sides by b, divide both sides by 4, so that I'm left with a is equal to 3b over 4. And that is my final answer. So at the point a equals 3b over 4, we will have a maximum value for the energy stored in the capacitor.